So yeah, we hard coded the board height to 20, and obviously it would be nice to be able to parameterize this number, but for the sake of just prototyping quickly, we just stick with it being hard coded. And so let's look where we actually set the view box for this stuff. So here it's 120 and height is 120 as well. So let's just quickly change this to 200 here as well. Save, go to the browser, and that looks already much better. It's still a bit cut off, so maybe we just spend another, I don't know, whoops, 50 pics. Okay, cool. So let's see, let's inspect the SVG element just to make sure it's really fully contained. Yeah, that looks a lot better. Although maybe actually how many columns do we have? Board width is 11 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're missing a bit in the width as well. So let's just jot another, I don't know, 30 on top here. Going back. Boom. That looks complete. Oops, sorry. Yeah, so I think the next step is I want to see some color in this, obviously. Draw those pieces that eventually drop from the top. So I thought maybe a good starting point is to parameterize the function that renders one of those elements to include a parameter for the color. And we see here the color is hard coded to gray. So obviously we want to have something here, and because I don't know, like I feel I don't want to be sending strings around for column through my whole program, so I'll just come up with a type for color, or maybe we call it field fill, because I also want to enclose the option that it's empty or it's blue or red. Let's put it like this, and we are going to add a parameter to our field fill function. Field fill. And I know already, like, this fill function from SVG attributes expects a string, and if I try to put in a value of my type field fill, then it obviously will scream at me. So I will I will implement a little mapping function like ff to color, and we can look at pattern matching to implement this. So I want to put in a field fill, and I want to get a string out, ff to color, ff, and we just write a little, whoops, here's a typo there, a little case statement. And I mean, pattern matching is not really interesting if we just match on the constructors of a type. So maybe later on we have a bit nicer opportunity to show the strengths of this. So, but for now we just say for each value, we say empty should continue to be gray, blue will just be the string blue, and red. So we just go with the predefined web colors here. And then if we want to tune the actual color values, then we just have to change this mapping implementation to hex values or whatever we feel like. So here we call the ff to color and just pass in field fill. So this feels like, and this, don't be surprised, this is just a standard reformatting that Elm format does, because it comes with this opinionated way of formatting files, which I really like, because then I don't have to care about it. So we are doing something wrong, obviously. So let's see what our compiler is complaining here about. Something is off with the body of row view, blah, 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 which is kind of expected because we are not passing in this new parameter. So let's just see field view row number in 127. So we are mapping a function over a list of numbers, and this function should be expecting only a number, but it is because we are not giving it enough parameters, basically. So let's just do the easiest fix to, maybe empty should also be empty. And this is another case of partial application. That's also a concept that is very common in ML-based languages like Elm. Like those languages, Elm, Haskell, F# are considered these functional languages that have some of the traits that I showed, and partial application is one of those very common patterns in this. So we are just going to basically take up the first parameter of the field for row function. Or actually, that's not the field for row. We changed the field view function. Where is it? Yeah, actually, it's bullshit. So let's undo this. Here we want to pass in empty. So does it compile again? Yes, wonderful. And we could also, instead of empty, just say red. And now the whole field should be red. Bingo. Okay, now also something that might also be weird to you is that I'm defining empty after using it here, which is in imperative programming language. This is usually a problem, or especially in interpreted languages, because we expect the program to step through this process and to assign this, but this is just strengthening a point that I also emphasized last week, that an Elm program is really not a lot of statements that get executed one after another, but it's really a list of expressions. So, and for expressions, since they're stateless, the order doesn't really matter. It just matters that everything is defined eventually. So it doesn't matter if I define empty or this local variable, because it's not actually a variable. It's just an alias basically for this expression that's on the right hand side of the equal sign. It doesn't really matter if I declare it before or after I use it in my let block here. Cool. So while it's nice to have some color in there, obviously we don't want to have all fields the same color. So I think it is time that we tweak our row definition a bit. Let's revisit type row, because we only have an empty row, and the empty row should really be only gray tiles. So now we have the two options, and I haven't made up my mind until now what option I go. What we definitely need is a non-empty row, to be very explicit, and this row should have a list of columns or a list of fields. Let's call them field, and a list of field is declared like this. So it's the question is, what value does it add to have a dedicated constructor or variant of row that is an empty row? And well, I know, but it's kind of hard to explain, and I don't want to just ramble on forever. So I'll just remove it for now, And we'll stick with a non-empty row is a bit a mouthful, so I'm just calling it a row at this variant. And then we can see where this breaks. I cannot find a field type. That's correct, because we haven't declared it. So what is a type? I would say type is an alias, because it's just a record basically. And how do we call it? We call it fill. And it's a, what did we call it? Field fill. Cool. Oh, there's directly type alias. What did I do wrong here? 37. Yeah, I forgot to actually name it. So that looks better. And I think I'm going to, just because it feels nice to have all the type definitions in one place, I'm going to pull up this type definition to up here as well, and it's a bit easier to see what is what. Cool, so that compiles. I cannot find an empty row variant in 59, so let's go to 59. Yeah, that's true. So make empty row. An empty row is a bit different now. I think it's basically it's or maybe no, let's I think I want to make it clear that distinguish between an empty field and all the other fields that have a certain color. So I think I'm actually going to make the type field not an alias, but an algebraic data type. So we have the empty field, and we have the field, and I'll just, because I don't think we need a lot of stuff in the actual field, let's just add a field fill as parameter for this constructor. So the row, an empty row, we said our board width is 11 fields wide, so we can basically map over a range from one, I never know if with the two dots if it's included or not, but also one off, it's not that bad in this case. And we create an anonymous function. We ignore the parameter, which is just the number between the 1 and 11 if we map over that range, and we create an empty field. So make empty row is only like a map always creates a list again. So we are mapping a function, the function, this expression here between the first parentheses set, and we're mapping over an array with the integers from 1 to 11. So while this might fix, it's not, this is Ruby syntax here. So let me replace this. Now at least it's correctly formatted again. So every time you see this red thing pop up, that's when my Vim plugin already can see that there's something it cannot parse the Elm file basically. So something is wrong with the format, the syntax, but that doesn't mean it compiles. As we can see here now, we still have a few compile problems. In line 45 and 39, I'm using empty. What did I say? 45. Boom. Ah, yeah, because well, actually, let's redefine this, because if we have a dedicated empty field, then we don't really need a color for this, or do we? I don't think so. Let's see if we can condense this right away while we're at it. Field color and field fill is kind of a weird name anyway. Then we have to revisit here. So let's say we just pass in the field. Oh, it's so catch up on my laziness here. Field. If it's empty, it's gray. And now we actually can see better the power of pattern matching. Because empty is okay as a value for field, because that's one of the constructors. I can just bring up the definition here again. Field. So this is the type we want to match against in this case statement, and one is field, so that's good. But blue doesn't match any variant of our type field. So we have to expand here a bit. We want to have a field with a value blue, then it's blue, or we want to have a field with the value red. So this is a bit better demonstrating what pattern matching does, because like we can really match into the objects, if you will. Cool. So also here we want to pass in a field. And 165, he's not happy with this variable that I just renamed. That's okay. I cannot find a map variable. So this is most likely because I forgot to import it directly. So let's see, where did I use map before? And I see like, okay, I used it by naming explicitly from which namespace this is imported. But usually I would say like we're using the map function. We will be using the map function a lot. And I'm a bit lazy to always type list.map. So that's why I will adjust how I am importing that. And I'm actually not importing it at all explicitly, and I don't need, because there's list is part of the core packages of Elm that get imported. We can have a look. Elm, list, docs. We see this is part, the list module is part of core, which is implicitly imported. So that's the only exception to that we have to import everything explicitly. But I can still export this exposing map, and now I don't need to qualify the map call. Okay, and the same thing for range. Range is also, and I think we used this last week as well already. So let's just verify range, and we see like, oh yeah, it's also used qualified. And because I'm continue to be lazy, I will just add this to my imports here. And now I can actually, whenever I call range, I can just remove the prefix, and the same thing for map. Let's clean this up right away. Map. Okay, cool. Let's save this, close this temporary window here. Cool. Now it's complaining about the first argument to field view is not what I expect. Empty field view. Let's see how we are calling this. Empty, empty, empty is red. That's correct. Should be field red. And rows is empty board. Something is off with the body of init. Rows empty board. The body is a tuple of type. Okay, so we're not adhering to our type declaration of our model. Let's revisit that. So our model is a board. A board is a list of row. And let's look at the init function. Make empty row. Where the board is supposed to be a list of rows. We are mapping over an integer list here, and we are making an empty row for each. So intuitively, like that's what it's supposed to do from reading what it does, but apparently it doesn't do it. So like I think I messed up this expression, and just like usually the error messages from Elm are really great, but they also depend on knowing the types. But as I said, like declaring the types is optional, and then Elm just tries to guess the right types, and now it's not sure, I guess, if it guessed it right or what it guessed is not matching. So it gives us this bit cryptic, and I think like probably I can figure it out by staring at it a bit longer, but I wanted to show you a neat little trick how to like make it a bit easier for us and the Elm compiler to find out what we mean. We can just make this a top level function and declare the signature for it. So make empty row is mapping something, is a function that is mapped over a range of integers. So we can just, that's why the function needs an integer, and it should return a row. I guess, no, that's not, no, yeah, that's right. Yeah. No, it should return a field, sorry, my bad. Because a row is made of many fields. So yeah, and we're still calling this here. So let's see if that makes the error message a bit more readable. Something is off with the body of make empty row. Ah yeah, now it's a bit more explicit. This map call produces a list of field, but the type annotation on make empty row says it should be a field. Ah yeah, no, of course make empty row should return a row. So that's the initial thing was right, was correct after all. And now we have even more concise error messages. This map calls produces a list of field, but the type annotation says it should be a row. Okay, that is very concrete. Like the intuitive understanding of a row should be a list of field is correct, but the question is does it match the types? And obviously it doesn't. So let's see what a row is supposed to be. And I still have the type definition here open on line 50. A row is a named type, so we have to name the variant. So we just pop in the constructor here, and because we don't want to wrap it in parentheses, we use the little arrow and just pipe everything into this constructor. And now happy, happy, happy. So if we don't want to pollute our global namespace with this function that we just extracted to be more specific our types, we can inline it again and delete the top level name, and it should still continue to work. No errors. So happy, happy, happy. Cool. So now we changed our implementation of a row. A row consists really of a list of fields now. So I don't know, we could do a little shenanigan here and say, instead of having 11, what is it, empty fields? Oh, why is it red actually? I thought I said it would be empty. Make empty row. Going to check our rendering function again. Empty is gray. Why is it red? Ah, because in row view, because we actually we're ignoring the actual stuff that's stored in our row. So that's good. Like, it's bad, but at least I know what's wrong. Field view for row. That's the function that we're mapping over our columns. Ah yeah, okay, cool. I think now that we have actually an object for each field or for each column in our row, we can throw away the hard-coded numbers here. And we can actually, instead of mapping over just the columns, the numbers of the columns based on our hard-coded value, we can actually map over the fields in our row. So here we have to deconstruct our row object into row of fields, and then we map over those fields. So now it will probably complain that the field view for row function is not compatible what we're passing in, because before we passed in integers and now it's fields. Exactly. So now we have to adjust our field for row function. So let's see where this is declared. It's declared here, and it's calling our field view function. So now this is a bit tricky because we actually need two things. Like, we need the index of the column to be able to know where we have to position our little square, but we also want to know the color of each fields. So intuitively, I would say this is a case for our friend indexed map, or what is it called? Yeah, list index map. Ah yeah, I think this is actually perfect. So just to bring the memories back, indexed map elm, we have a look at the documentation. So it's very much like map. It iterates over the list of A's and produces a list of B's, but the function we are applying does not only take the A from the initial list, but also the index, the position of that element in this list. So we might have to rearrange the signature of our rendering function a bit. Field view from So let's just call it, since I haven't exposed or like explicitly imported the indexed map, I have to prefix again with the explicit namespace. And we want this function now. Maybe actually we do the same exercise again just to flex the muscle. Flex for row, and we're going to write it a bit like this. It will take the index. It will take a field, and it will produce a HTML message. And like, this is our transformation function for our indexed map, and we will put in a list of fields, and we will get out a list of HTML message. Okay. So let's call this just F for the sake of brevity, and fields. No, this is actually bullshit. I only want this. Like, this is the signature of the whole indexed map call, but I only want to declare the actual function that we're going to use to map over this. So this is the column index, and this is the field. And now we can try to call our field view function again. And maybe we can inline some of this stuff later, but just to be a bit more explicit about it and to eventually get better error messages from the Elm compiler. We are a bit more expressive about what we actually want to do. So let's look at the field view function here in the other buffer. If I manage to type it out, where is it defined? Here, bring that up. And we are going to pass in field a row. We are missing a row and the column index. So I think row is really another int here, the row index. Let's be a bit more explicit about this as well. Row index. So we will throw away this here and make use of the nice partial application function again. What is row? Int row number. Oh, I'm using a different identifier each time, but you just have to deal with it. Row number. I'm probably going to suffer from it the most, so let's see. Cool. That looks to me like it should roughly line up. Let's see what the compiler says. Oops, I didn't mean to close it. Oh, it actually, no, it does not compile. That would have been too easy. In 130 cannot find a row variable. That is correct. This is what I called row index. And here we go again. And it's gray again. So that's great because now it's reflecting what we're actually doing in the data. So yesterday we started, last week we ended with a blank board, and today we made great advancements by still being able to render an empty board. Doesn't look like it's a big improvement, but it will actually enable us to address, if you will, dedicated fields. So addressing dedicated fields also comes with the interesting question, like where's the origin of our coordinate system? Like there are multiple options. We could start in the top left corner, like this is usually for screen coordinates the case, but I feel it's most natural to start with Tetris in the lower left bottom corner, because like I feel the row on the bottom is the first row, the lowest row, and it makes just sense to assign it the lowest number as well. So maybe just to showcase how we are able to address a specific field on our board, why don't we take the board and turn one of those squares and fill, in our speak, one of those fields. So let's see where are we creating our empty board in the init function. Where is it empty board. So instead of initializing with the empty board, we want to have board with one field. So let's just create a function. Actually, let's use the type system to express our intentions. Board with one field, or let's say we want to have a function that set field. It takes let's call it a position and a field color, and it takes a board and it returns a board. So my intention is to take the board that we pass in last and a color and a position and set the field at this position on this board to this color. Okay, so let's go get at the implementation. And let's be very naive. pos color board and just return the board just to get it compiling again. And it tells us, yeah, I don't have a type position, which is absolutely correct. So let's define a type alias position, because there won't be any variance for a position, so that's why we can use it in alias. And we can just use this special syntax to denote a tuple, and since we only have whole numbers for our x and y coordinates and on our board, we can just say this is a tuple from int, compiles again, happy, and let's call this here set field 0, 0 color. Let's take blue for a change. So, oops, I missed the open parentheses for position. So this should compile again, and it doesn't. Something is off, and I don't know why. I feel this should be correct. Empty board. Why you no compile? Okay, let's just do the old trick again. Can we? Well, let's see. I don't know what type empty board. Like, I would expect empty board to be a board, but maybe I'm a bit naive here. Let's check the type declaration of board again. Type board does not exist, so I guess it's an alias. Type alias board. Aha, okay, but it's this. Ah, yeah. I see what happened there. So actually, we're creating kind of this key value thingy where we actually say rows is this thing. So let's quickly back up a second here. So actually this expression in the squiggly brackets, that's the board and not this. So this is actually a bit misleading what I did here. So I will just fix this by saying like, okay, this rows is this is the row empty board. So now I can update this expression to actually say board equals empty board. So this should compile again. Wonderful. And now we can say set field. Well, let's say not 0, 0, but 1, 1. Blue empty board. So this should still compile. No errors. Wonderful. But also no blue square. And that's because we are not actually doing something to the board here. So something we can do here. Oh no, let's just stick with that. That's okay. So what we now need to do, let's have and open a block for local expressions. So we want to create a new board, right? And the new board is based on the old board, but has rows equals new rows. And then we return new board. So again, we can use something like pattern matching or deconstructuring here, where we say like x and y, and this y we're directly assigning these portions of the tuple to those local variables like this. So, oh, new rows, there's a typo. Fix this quickly. So now we need to compute the new rows of the board. And again, we cannot update or mutate the existing rows object. Like, or we could even just for readability, we say old rows is board dot rows. So we cannot mutate this, but we can compute a new array of rows that represents the desired state. So if we want to create a new array based on an old array and it has the same length, then this screams map all over again. So I know already we want to do something with map. And there's a function, let's call it update row. And we want to map over the old rows. And so if I'm just saving to get the, oh no, I don't even, if it doesn't, oh, I'm having some syntax problems. I just wanted to profit from the fixing my indentation, but it's not happy with line 64. Oh, yeah, because I'm missing an equal sign here. Okay, now at least it's nicely formatted, but the compiler will tell us, oh yeah, we haven't defined update row. So what is it supposed to do? So again, because it's a bit more complicated, I'm going to write out the signature first. Update takes a row and produces a new row. So that we know for sure. So the idea is that if the position that we pass to set fields is inside of the old row, then we want to replace the field at the column that is denoted by the X component in our position. Then we want to replace this with the field of this color. So we definitely also want to have the position. So now we have the position that we want to change, and we have a row, and now we want to compute the new row. And so to find, like, the first thing we have to do is find out if the Y component in this position here, if we're at the current row with that position. So, but if we look at the type definition of a row, type row, then we see, oh, a row is just a list of fields. We don't really know at what position we are. So we need also somehow need to know the row index, which is an integer. So let's quickly update this, X, Y, and row index. Okay, and now it gets a bit more interesting, right? So we can already say, like, if Y is not equal row index, then we don't want to update the row. So we can just return the old row. Else, now our old row again is a list of fields. So now we want to update the field at the position X in our list of fields with the new color. So we also obviously need the new color. So let's just, oh yeah, field color is the type name I chose for that. Field color. Let's pass this in as well. New color. So, and we have again, the row is truly only what's contained in a row is a list of fields, and we want to turn it into an updated list of fields where the element at the position X is exchanged with the color of the desired, with the field of the desired color. So it's a map again. So we again update field over row. A row is truly is this, so we can just, instead of trying to grab this out there in our implementation body directly, we can just pattern match into fields. So we want to map over fields, update field. Cool. And yeah, we need to define update field. So update field, again, the first thing that comes into update field is one of the elements in fields, and fields is a list of field. So update field definitely gets a field and is something. But again, the field itself, if we look at the type definition of field, it does not know at which position it is. So we also want to have the field position. And so to get the field position from fields, we need our other old friend, indexed map again. So this way, our function signature here is already correct, like at least it will match up with what Elm is guessing for it. And we can say if field position is X, then we want to return a field with the new color. Else, we'll just return the old field. And so something also, a mistake I often make is the syntax for the not equal operator in Elm is a bit different. It's the slash equals and not the exclamation mark equals. Okay, let's see if that makes logically sense by running through it. We have a function that takes a color, an XY position, the number of the row we are currently investigating, the content of the row we are investigating, and it returns an updated row, or eventually updated row. We just say if the Y component is not equal the row that we're currently investigating, we can return early and just say like, well, we're not changing the row at all. But if it is, then we are looking at each field in the row together with its index and apply the update field function. The update field function takes the position of the field in the row, like the column, and the content of the field. And again, if the position we're currently looking at for that field equals X, then we want to replace it with the field of the new color. Otherwise we return the old field. So that makes logically sense to me. I probably have still some mistakes in there. And of course, 58 update. What are we calling here? Yeah, update is a bit too generic name. Update row. So that's better. Old row cannot be found in line 68. Old row. Oh yeah, that's correct. We can just say as old row. This way we have access to the deconstructed fields value and the combined value. So that's better. And in line 81, second argument to map is not what I expect. Okay, so our update row function is not really applicable to what map expects. Line 81, bring that to the top. Let's look at this again. Okay. And I'll just bring up the update row definition here in the other. It's already there. Okay, so update row, like I know already a map always turns a list of A's into a list of B's. So the function that I'm passing here, the mapping function, should only need an A, so a row. And we see our update row needs a lot more things than just a row. But luckily, like field color and position is exactly what we have here. So actually I will remove the destructuring here and call it just position. And we can do another application of partial application, or meta partial application. So first thing is the color. Let's put this in. Second thing is the position that we want to update. So we give this as well. And now we still have two parameters to fill, an int and an row. And again, this signature, it's not, didn't choose it, well, I choose it intuitively right, apparently, because we don't want just the row, but the index of the row again as well. So let's, it's again a case for our indexed map. And since I was too lazy to add it to my imports, I have to qualify it explicitly. Ka-ching! Something is off with this if expression in line 71. Let's have a look. If we want to return a row, and this is definitely a row because that's a row that we pass in, but list index map will obviously return a list. And while, like, I'm starting to regret that I created a variant for row, because there's only one variant and it could be alias to a list of fields. But let's, for the sake of just to getting it to compile quickly, call our row constructor, pipe in the list of fields, and wonderful, we have our blue square. Yay! It just, by our definition where we want to have the origin, it seems to render our field upside down. So let's make sure that we render it the right way. So let's go to our render function and just fix how we calculate our y offset here. So I say we just do 11 minus, probably off by 1. Let's see. Yeah, I resort to try and error a lot in those cases where I'm too lazy to actually do the math. Times 11, yeah, that's wrong. That looks a bit better. But something is off with my math there still. Let's so the first row, $150. First row is at Y121. We don't have 11 rows. We have. Ooh, what's happening? Yeah. I know. Do I have a constant for our board height already? Maybe it's a good time to start with that. Board height. Let's just elevate this to a global constant. And I know some people might raise their eyebrows now and be like, oh, global variables, they're evil. But the evilness from global variables comes from the fact that people alter or mutate them from various parts of their program, and that if the program grows, it's hard to trace who changes this variable when. And the nice thing about Elm is we cannot change variables. We know if we have board height equals 20 at one point, we will have it for all eternity, basically. So that's why it's an order of magnitude less evil to have a constant like this. Or significantly, if at all, evil. Boom! Wonderful! So just to see if our function actually does what we expect it to do, we can call it again. Set field, where are we calling it? And I'm just going to call it again on the previous result. set field, let's call it at 5.3 with red, and type in the result of the previous call. That makes me happy. Okay, cool. What time is it? We spent a good half an hour, so I think that's enough time for today left to try to do another step. And I think the next exciting part would be to look at the tile definition. And for this, I really had a look at how what's his name? Sean did it. And you see, like, he does a lot of similar things to what we have just done in Elm and ClojureScript. He creates a board, and then the next step is right away creating the pieces. And the way he defines the pieces is he uses a list of relative coordinates to a local origin or a local coordinate space, if you want. Like each tile has a 0, 0 point and defines the rest of the pieces relative to that origin. So my favorite piece is the T piece. So that's what I'm going to start out with as well. And as everything good, our way to implement starts with a new definition, type definition. Let's call it a piece definition. Definition, because it won't be like these are not the actual pieces that we are going to have on the board. It's only the definition of how a piece is looking like, and then I think that's fair enough as reasoning to give it a separate name or call it definition. And since the types for the type of a piece definition, we won't have variants. We don't need a algebraic type. We just say a piece definition is a list of, and since we already have a type for tuples, like those are truly positions in a different coordinate space, but they're still positions, we just say it's a list of position. So I don't expect any compiler errors on this. So let's define a constant for the T piece. It will be an array, as we said. And there will be the coordinate 0, 0 in it. And now we just declare the pieces that are around the center. And we know in our coordinate system, in our board coordinate system, the column numbers go up as we move, the row numbers rise as we go up in rows. So this piece, this tile over the origin would have the x coordinate, the same x coordinate as the origin, so 0, 0. And the y component would be 1 higher. And here you see Sean made a different design choice by having the coordinate, the y axis inverted. For him it goes up in the negative direction, but to each their own. So for us this means x is 0, y is 1, and then we have 2 more tiles in our piece, one to the left, one to the right, both at the y coordinate 0. So let's add 2 more rows into our array, one to the right and one x minus 1, whoops, to the left. Let's do format to the formatting. So now we have 4 pieces or 4 tiles in our piece definition. That looks good. Cool. So now what I want to do next, let's see what Sean does. Yeah. So John creates the initial board. Rotate piece, tank progression. Okay, So actually this is the next piece I'm interested in. I want to be able to place the piece at a position on our board. So for that, it's not only enough to know the piece definition, but we also need to know the position of the piece to be able then to color the board in that specific position. And next to the position, we also obviously need to know the color of the piece. So I think that's reason enough to extend the definition of our piece definition. And I would argue, like, let's just add a signature here. This should be a piece definition to let the Elm compiler help us a bit, but it's not enough that our piece definition is a list of position. We also want to have a color, since in classic Tetris, each of the different tiles, pieces, has one dedicated color. So the red, the T is always red, for example. So let's enhance our definition to, let's call those things tiles that we just defined, but we also want to have a color of type field color. So if we compile this again, then the compiler will hopefully complain to us that our T piece is not really a piece definition, but a list of this, which was our old definition for piece definition. So let's fix our implementation of this. Tiles. And add the color. What did I say? I said T's are supposed to be red. And this colon has to be an equal sign. And let's format it nicely. And now it compiles again. So that's nice. That's cool. So now let's try to get one of those T's into our board. And for that, maybe we start at the view board function. Do I have a function like that? No. Board view. Oh, yeah, close enough. So the board view renders a row view for each row on our board. So what we want to do eventually is to calculate a new board. Maybe we just call it, like, I want to place T on board. Very naively call it exactly this. We are going to take a position where we want to place the piece, a piece definition, and a board, and return an updated board. Place on board. Position. Piece def. Old board. And for the sake of having it compile, just return the old board, so it doesn't really do anything. So for our board view, board with piece, let's call place T on board, and let's place it at 10.8. Piece definition is T piece, and board is the board. So then, instead of rendering the row views on the board that we pass in, we want to render it on this board with piece. So I hope it's at least there's no compile error. That's good, but it also, the T doesn't show up. So that's because we didn't really implement our place T on board function. So let's start out by making some space for local definitions. New board. Or let's say old board with new rows. Cool. So new rows, and again, like rows is truly a list of fields. No, a board is a list of rows, and a row is a list of fields. So for each row, we want to find out if we have to color in any of those fields that match the piece definition at this position. So we already have a function to color in a specific field. So for now we can just, or do we use it? Do we use it? No, we don't use it. And I'll explain in a while. Maybe I explain directly. We could use our set field function. I'll just quickly bring it up. Set field, that takes a position, a field color, and a board, and just call it for every position of our piece definition. But each time we call set field, we are iterating over the whole board, which is not really efficient. So what I rather want to do is iterate once over all the rows, and if my rows is in the range of positions that I get by translating the piece definition to this position, then I want to look closer into those rows to see if I have to update any of those. So let's do this step by step. Like the set field was nice to verify our data model works correctly, but I think for this application it's not the best use case. So we know, again, as I said, like I want to iterate once over the board. So iterating once over the board screams, again, map, or more precisely indexed map in our case. So we need another update row. And I think we cannot reuse this name because we already have a top level function that is correct. Oops. So update or update with piece. Let's call it this. And we want to map over old board dot rows. So cool, that should be fine. And we can again do a little placeholder definition here just to make the compiler happy and see that we're on sane grounds. And update piece will take a row index and a row. I know this because I know something that I'm transforming with indexed map will take the index of whatever array I pass in or list I pass in, and one of those items in whatever collection I'm passing in here. So this should be good, and I will just return the row just to make sure keeping the compiler happy. No compiler messages, so that's good. Cool. Let's blow this up. So what I want to do is, like, I know if I transform, the piece definition has its own local coordinate system if you want. It's very local around the 0, 0. But obviously if we want to place our piece at 10, 8, then I cannot compare the coordinates in my piece definition with these absolute board coordinates. I kind of have to translate or transform the piece definition to the position. And if I do this, I end up with, because our T piece has 4, or like for each tile in our piece, I basically have to add this position. And then I know which position each tile of our piece wants to take in our board. So let's start by doing that. So let's call them absolute tile positions to be very explicit. And again, I want to transform each element in a list to a new element in a new list of the same length. So again, it's a map. And I'm just going to put a placeholder here. And we want to map over the tiles in our piece definition. Piece definition dot tiles. So as I called it, translating these tiles, I will just use translate tile as an identifier for that function. Translate tile, and again, this is a mapping function over a list of tiles. So each this function has to receive a tile as a parameter. So and a tile is truly, let's look at what a tile really is. Piece definition, type alias. Piece definition, okay, piece definition has tiles and a color. So that means, a tile, what is a tile? Is just a list of positions. So what we're mapping over is a list of positions. So translate tile needs to take a position, and we can deconstruct this into tx and ty directly, prefixing in case I need xy as other variables again. And translating really truly means only that we're adding, and that's here, that's handy to have x and y still available, because we will calculate the translated position, which is truly just tx plus, or x plus tx, it doesn't really matter which way around, obviously, y plus ty. So this is our little helper function that translates one piece of our piece definition into our board coordinates at the position that we are putting into our higher level function here. And we're mapping our absolute tile positions. So that means absolute tile positions is now an array that has the same length as the tiles in our piece definition. So in our T piece, that means we have 4 coordinates that are translated to the position. So that's good news. And now what I usually try to write my early return statements first. So if I know already I can ignore some rows early on, then I'm trying to write this down first. So this means basically I know already because I've written the tile definition, or we can look at the tile definition again in Sean's presentation. Where was it? Here, our T piece is occupying 2 rows. No matter where I place it on my board, it will try to occupy 2 rows, and all the other rows I don't have to update, so I can just return them. So what I'm doing is and since I know a piece doesn't have holes, I can just compute the min and max row of the positions that my piece wants to take on the board. And if my row index, when I'm iterating through the whole board, is lower or higher than the max min, then I can just return the old row. So let's say min row taken is, and we can, like, basically I'm going to take all the y positions from my translated piece, and I'm going to take the lowest one from this. Min row taken is, so I'm going to map, I'm going to create an anonymous function that takes a position, so it has an x. Oh, now I have to xx and yy just to not override any local variables. And I'm returning yy. And I'm mapping this function over our absolute tile positions. So this is obviously not the complete definition. So now we just have the array of only the y coordinates of our translated tile. And now I want to have the minimum of this. Minimum. And I would kind of expect that there's a function for this in Elm. So let's go back to our just documentation minimum, and that's great, but something is a bit weird here, because we see a minimum of 3 to 1 does not just return 1, it returns just 1. And that's because it's again a safety measure that we get with the type system, because we have to make sure that we can always return something meaningful. So in the case where nothing prevents us from calling minimum with an empty array, and there's obviously no minimum in an empty array, so we get nothing in this case. So this is where it feels a bit cumbersome if you come from languages like JavaScript or Ruby, where you just get nil in this case. But in the end, you will end up doing the same. Like if you get nil, then the minimum that you still have to deal with this case. And by being explicit about this, by returning a maybe, the compiler can force us to deal explicitly with this case. So we just have to qualify list minimum. But again, minimum row taken, like we know, we will always, like I have a hunch I just want to return the number null in this case, or 0. So if list minimum returns nothing, then I just want to default to null. I know it's not going to happen anyway, because our tiles will always have a position, but I just have to be explicit about this. So let's look at maybe. And I think there's a function called with default. Exactly. So the function with default takes a value. It will be an integer in our case, because our array is in a list of integers. And it takes a list that is maybe an integer, but it will always return an integer. And that's what we want to do, because when we deal with this minimum, we don't want to deal with the maybe case. So I will call, and just put it on a new line, maybe with default. And since maybe is also part of core, we don't have to explicitly implement it. And now we can actually break it on those pipe operators. I don't know what's the official name for this. Should look this up. It's complaining about line 183. That's probably somewhere else. So let's fix this. This doesn't do anything yet. So okay, cool. Now we can try to indent it in a way that's a bit more readable. Oh, yeah. Isn't that pretty? So we're mapping the y value of our absolute type positions, and because we are not using the first element of the tuple, we can also just replace it with an underscore. Or no, actually I still have, it's getting dark here, and I'm not a good typer. So we could rewrite it like this, just because we are not actually using this. But actually, tuple is, as I said, is a data type that comes with core, and very conveniently it's here in the range. And you see that we have actually convenience methods for accessing the first or second element of a tuple. So instead of writing this function in this cumbersome way, we can just replace this by saying tuple.second. So this also reads a bit better. So we are mapping we're taking the the second element of this list of tuples. We're finding the minimum, and if it's if the against all odds this list is empty, then we are returning 0. Otherwise, we are returning whatever is the lowest element in this. So it's a bit of duplication, but I also want to finish this today, so I'm just going to duplicate this because we need to do the same thing for the maximum. So instead of minimum, we are calling maximum. Maximum. Min rotaten, max rotaten. Okay, now we can go back to our update with piece function that is supposed to iterate through each of the row with its respective index and try to determine if it needs to update the row or not. So now we can say if update with piece. Now I have to think a bit what exactly is this what is this supposed to do? We have our absolute time. Yeah, okay. So we can already say if our row index is higher than the maximum or lower than the minimum, then we can just return the old row basically. So if row index is smaller than minimum or row index is larger than, and we called it max row taken. Max row taken, then min row taken, else row. So now I didn't really do anything because I'm still returning row in both branches. I just want to make sure we are still compiling. We are, so that's great. So now to the more complex case where we actually have to update the row. So then we turn, this is the positive case or the negative case where we would just return the old row. In the new case, in the case where we do have to update. So that means we have we know we are in a row that needs to be updated, and we have the list of tile positions that are being taken that we now want to color in basically. So that means we have a row at hand, we have a list of positions that we color in. So we want to say color in positions. And we want to give it, well, we do have the absolute, how do we do this? Color in positions, and we give it the current row. And we write a little local helper function. Color in positions, it takes a row. And since we can access all the variables like absolute type positions here, we don't have to pass everything in explicitly. So now what we want to do is we want to figure out if for each field in our row, so we can actually already deconstruct this to row fields. We want to do something for each field in our row, so it screams map all the way. We want to map over fields, and we want to do something to each field. Let's call it color field, and we are going to declare a little local helper method again, and color field, and we need the column index, I'm pretty sure, and we don't need the field itself because either we are if we need it, if we don't want to change it, we have to return the current field value. So, and because we want to have the column index from this map, I can already tell by having it done like 3 times today already that we want the indexed map, not the plane map. Okay, so we like basically if I want to say like if the position of the current field is in the set of absolute type positions that are taken by our translated piece, then we want to color it in. So I'll just leave the complicated stuff out again to write complete the if statement. So if field is in blah 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 positions, then we want to color in the field. So we want to return a field of the color that our piece definition has. So finally going to kind of close the loop here. And if it's not in this range of tile positions, then we just return the unaltered field. So if, how do we gonna call this? If contained in taken positions. Today is the day of long identifiers. So how do we determine this? Contained in taken positions. So for that we need to know px and py, or fx and fy, because it's the x and y position of the field. Nice excuse to prefix with only one letter. So now I want to know if this position is contained in those. So I'll have to iterate through this array of absolute positions and compare each of them against if they match this. So maybe there's like a find or a find first function in the core library. Let's say find. No, I guess we want to filter. Yeah, okay. So the way to go is to filter the array of taken positions with a predicate and then see if this list is empty, basically. So we want to filter do I write this here as a nominal function, or like, let's give it a name. Positions match. And we want to iterate over the list of absolute positions. So that will give me all the positions that are the same than this position. But I'm only interested in, are there any? And I think there might be even a any function. Wonderful. So we have, oh yeah, actually we don't want to filter, we want any. And because I haven't imported it yet, I have to be explicit about this. So we have to implement positions match and positions match takes one of the whatever is in here. So let's call it again tx because it's a taken position, ty. And does this make sense? Ah, yeah. Positions, no, it takes actually two tuples. That's px just to have something else here, and return true if tx is the same as px and ty is the same as py. So cool. So this positions maps is really just like a or equal position, maybe a better name, equal pos. And we will have another case of partial application, because here we are going to bind this thing that we... No, where are we? Okay, let's disentangle this a bit more. Well, does it compile? I would be surprised. Indexed map. No. I cannot find an indexed map variable. I thought I imported this. Okay, I have to turn on the light here. I cannot see my keyboard. That's better. Indexed. Ah no, apparently I did not import it yet, so let's just go with the qualified name here. Color and position row 20210. Okay, like this is growing a bit. There might be some need to clean this up later on, but let's go back to from the top down, basically verify our intention. We want to update the rows. For each row we want to update with piece, and update with piece takes a row index and a row, so that signature looks good. If we are outside the range of affected rows, we just return the old row. That looks good as well. Otherwise, color in positions row. Okay, color in positions row takes one row and should return a row. Ah yeah, and I know already what's wrong here. We forgot to construct a new row. Let's see, that makes it happy. Not yet. This if condition is not very true or false. Oh yeah, okay. Contained positions in 197. Contained in taken positions. Where do we call this? Here. Ah yeah, contained in So I feel column index is the next position, so column index. What's the Y here? Color and positions. Where are we calling color and positions? Row. And we want to pass in the row index here as well, because that's what we need to be able to compare if we're in the right row. And it will yell at me that I have too many local variables with the same name, but let's just have it yell at us. Let's close this other buffer. So if contained in token position, taken positions, and that's our current position. Yeah, that makes sense. Then we update it, otherwise we return it. Woo! Does not have completely the shape of a T, but at least we have identified the right rows, so that's good. So tx equal pos. So for some reason our detection of the exposition is not right. Contained in, like, apparently it returns contained in taken positions for every field of the rows between min and max. Column index, what is column index? It's passed into color field. Indexed map, okay. Ah, I see. I'm saying the positions are equal if X or Y are the same, and that's obviously wrong. So both has to be true, the same. Et voila. Like at least it's a partial T. Maybe we positioned it a bit too far to the right. Yeah, our board is only 11 columns wide, so let's say it's here at 2, 8. Nice. Wonderful. Cool. That took a bit longer than I anticipated, I have to admit. But at least we can place a piece, like we can also just call it a second time. Or maybe just to reward us all the abstraction work that we have been doing, we're going to define a second piece, maybe the J, and place it on the board as well, just to get this feeling of accomplishment. T piece, where's the definition? We are going to just bluntly copy this. J piece, J piece. It's going to be blue, that's for sure. And we definitely need our origin for the piece again. And we have one piece that's in the same row and one to the left. So it's -1, -1 and 0. We have one piece, one tile that is to the left and one up. So it's -1 plus 1. -1 -1 plus 1. Oh, I'm really running out of typing ability. And we have one that is one to the right, but in the same row. So like this. Still compiling. Yes. And where are we placing our T piece? Place on board. Board with pieces. Place. Okay, that sucks. Place T on board is, well, actually it's only the wrong name because I can just still throw in the J piece here. And we are going to place it 5, 11 or 13, that there's at least one row space between. And then we're going to render it the board with pieces here. And it's not working. Did I save? Oh, okay. Ah, yeah, that's an oversight because we want to compute the new board based on the board that already has the T piece. Yay! Cool. All right. So today I learned when you talk while you type, it takes a lot longer to implement this stuff. I don't know. Should I go over this implementation again? I think I just renamed this function to place piece on board. And I'm going to write a bit a recap. Don't know yet which aspect I'm going to focus on, but I think this function makes a good candidate. Maybe I just refactor this function a bit for the blog post and while explaining what each of those pieces does. All right, that's it from me for today. Looking forward next week. What are we going to do next week? Like next week, either we are going to implement the gravity. Like let's have a look at what does Sean do. So we have a few options. Obviously, what's missing? Initial state, blah blah blah. State progression. The nice thing is I can be really egoistic. Soft drop. Like when does he do the gravitation? Collapse rows. I think add gravity. Oh, it comes in the very end. What can I do here? Ah yeah. If I mouse over, then it's falling. We can do either that. Yeah, I think I feel like doing the gravitation next week. Cool. All right. Thanks for staying with me and see you next time.